Hello, welcome back. This time I want to do a mock midterm for the machine learning concept that I made previous videos about. So really I would just show like a question, maybe talk about the question, and then the next slide would be the answer. Or if I guess the best way if you want to do this would be to pause on the question, then try to work out yourself and then see the answer and the explanation for the answer. So let's go ahead and start. So let's go to part one. Talking about similarity and normalization. Question one, binary similarity. So consider two binary vectors representing user purchases. So one equals bought, zero equals didn't buy. And as you can see, here are the two vectors. Now calculate the matching components. Both one, both bought it, both zero, both didn't buy, and then the mixed matches. And then that's part B, which is calculate the following coefficients. Show two decimal spaces. Calculate SMC, or simple matching coefficient, Jaccard, and cosine. So if you want to pause and then we go over the solution, going over now. So let's break down how we solve this. So this question is all about measuring how similar two objects are based on binary attributes, like whether a user bought an item or not, right? So for part A, first, we need to count the matches and mismatches. So we do this just by looking at the vectors, just the index. So both one means they both bought it. As you can see, there's only two instances where they're both one, right here and right here. So the answer is two. Now for both zero, there's only two instances too of those. And then their mixed matches where one bought or A bought and B didn't. There's two of those where A didn't buy and B did. There's only one of those. Totaling a seven, right? So that's that for part A. Now for part B, we took some of these answers and plugged them into SMC, Jaccard, and Cosine. So let's talk about the first one. So simple matching coefficient, or SMC, only cares about really cares about matches versus total attributes. So it treats both zero as a valid match. So we add both the ones, so it's two ones, and the zeros, two zeros. Gives us four divided by the total attributes, which right here we calculated to be 7. So 4 divided by 7, roughly 0.57. Now, if we take an exam or a quiz, and I say use SMC when negative matches, like what you didn't buy, are just as important as the positive ones. Now, Jaccard. So Jaccard is different, right? In Jaccard, you don't really care about like the thousands of items that you didn't buy, right? So Jaccard ignores the 0, 0 completely. So the numerator is the intersection 2, right? And the denominator is the union, the 2 plus 2 plus 1. So that gives us 2 over 5, which is 40, right? So we get the matches, 1, 1, and then the matches plus the mismatches. But remember, we don't include the 0, 0s. We don't worry about that for Jaccard. And we get 0.40. Now for cosine similarity, this measures the angle between the vectors. So the numerator is the dot product, which is binary vectors, just m, the shared ones. So that's 2. The denominator is the magnitude, the length of a times the magnitude of 4. So a has 4 ones. So its length is the square root of 4 times b, which has 3 ones. So which is square root of 3. And that will be 2 times 1.73, as you can see. And 2 divided by that will give you about 0.58 roughly. Now let's move on. We're still on part one, similarity and normalization. This time we're talking about z-score normalization. So you have a data set with two attributes, age and income. You got the population mean vector and the standard deviation vector. Now normalize the following two data points using z-score normalization. So for point A, you have 30, someone who's still 35, and the income is around 40,000. Point B will be 20, and then income is 70,000. So just pause and remember the formulas to use this. Here's the standard deviation and compare it with the mean. So remember to compare it with the means vector. I'm going to the answer now. So here's our formula up here. And here's actually being done right now. So if you remember normalization, it's a crucial step before feeding data into many algorithms like neural networks or like k-nearest neighbors. So we're using z-score normalization, also sometimes called standardization. So the goal here is to recenter our data around zero and scale it relative to the standard deviation. Basically, we're asking how many standard deviations away from the average is this specific data point? So for A, the age the so person was 35 years of age, and the mean average was 30, right? Difference of positive 5. What was 5 more? Since standard deviation is 5, they're exactly one standard deviation above the mean. Look at the income. They earn 40,000, which is actually 10K less than the average. So since the standard deviation is 10K, they're exactly minus one standard deviation below the mean. And we calculate it here actually. We would just do 30 whatever the actual age was, 35 over minus the mean over the standard deviation. So here 5 equals 1. We do the same for income, but instead you use 10,000 and use 50,000. You just plug in and you get -1. So your new A is 1 or -1. Point B, same thing. They're 20, or this person was, their data set was 20 and 70,000. So just plug in 20 minus the 30 over the 5, then 70 minus the 50 over the 10,000. And you would get 2. So the new vector for B was -2 and +2. So I want you to notice how originally income, right, was in the thousands, and H, which is just a double digit. If we did it normalized, the income variable would dominate the distance calculation just because the numbers are way bigger. Now, as you can see, both age and income are on exact like, same scale. They're both roughly between -3 and 3. So that's why you would normalize. Still in part one, but this time, so actually we're using the new A and new B that we got from previously. So keep these in mind and find the distance between them using L1 or Manhattan and L max Newton. Now, before you start to remember, Manhattan is not really as like diagonal line. It's like you're walking Manhattan. You have to. So if you're trying to find the distance from like point A to point B, and you're walking blocks, you mostly walk up, like like you're walking in Manhattan or just any city. It's not just like a straight diagonal line. You're going straight, then you make it right, then a left, then maybe a left, and whatever, something like that. So that's basically a one. Oh, actually, I have the equations down here actually. So let's go to the answer. So let's go through it. So first for L1, we take the absolute difference of the first like dimension, age. Remember, I wrote them up here too from push it two. The new A was 1 and -1. So we first start with the age, which is just the 1. Age, the 1 minus the -2, this -2, the B -2, which should give you 3, added to the -1 minus the -2, which would give you -3, but you have to get the absolute value of it. So you wouldn't add 3 plus -3. You instead would add 3 plus +3, which would give you 6. Because you're taking the absolute value. So if the answers here you got are negative, they will be positive. You have to turn them into positive or change them into positive. Now for the L max norm, Think of it like a king moving on a chessboard. A king can move, diagonally, horizontally, or vertically. Because it can move diagonally, the number of steps it takes to get somewhere is determined purely by the longest single dimension. So we look at the differences we just calculated, right? 3 and 3. So the age difference is 3, the income difference is 3. Since both are 3, the max is just 3. Now, let's say in a world war scenario, if the age gap was 10 and the income was 3, then the answer would be 10. So for this one, you basically just try to find the max distance. Since they're both 3, the answer is just 3. Now, new part 2, k-means clustering. So here's question 4. Consider the following distance matrix between 5 points, A, B, C, D, and E. We are running k-means with k equals 2. Initial centroids are chosen as point A and point C. So part A, determine the initial allocation of points. For each point, B, D, E, is it closer to A or C? Centroid A or centroid C? For this one, you're really just looking at this. I can actually probably walk it through here. So first, how you will walk through this, and you look at, like, let's say look at point B, right? Let's look at row A or column for B. The distance is 2, right? Let's look at C. C row or column for B. The distance is 6, right? 6. Now 2 is smaller than 6, so team B, no, so B would join team A, I'm sorry. So A would join team B would join team A. Now you look at the next point because it's B, D, and E. So let's look at D. So D, distance to A is 3. Distance to C is 5. 3 is smaller, so D will also join team A. Now the last one is E. So E, distance to A is 7. Distance to C is only 4. So 4 is smaller, so E joins team C, right? And then basically the same thing that I did here. So now you have, for team A, you have A, because the A, A is part of A, B and D. And for C, you only have C and E. And that's it. There's really just, if you get a question like this for the quiz or a test, there'll probably be more to it. You'll have a part A, then a part B. You'll be doing stuff with it. But for part A, we're really just looking at this and looking at the distances in which team they would join. Now, we're actually going to use these answers for question 5. Reconstruction error. Using the clusters you formed in question 4, calculate the reconstruction error, total distance for the system. Just a hint, sum of the distance of every point to its assigned centroid. Make sure to pause, and this is actually pretty easy once you know what you're doing. I'm just gonna go to the answer. So basically, this is basically asking just how bad is our clustering, right? If our clusters were perfect, every point would sit exactly on top of its centroid, and the error would be 0. The farther away the points are from their leaders, the higher the error. So for cluster 1, which was centered on A equals A, we sum all the distances of all the members A, B, and D to the leader A. So A is only 0 away from itself because A is A. And B is about 2 away. It was 2 away from A, and D was 3 away from A. So you sum all of those together, 0 plus 2 plus 3, and you get 5. That's the error, the cluster 1 error. For cluster 2, you do the same thing. You only had 2, C and E, so C is 0 away from itself, and E was 4 away from C, so 0 plus 4 equals 4. The total system error was 9. So you might think, what does that matter? When you run k-means in real life, the algorithm tries to minimize this number. If we ran this again with a different starting centroids, we might get a total error of 8 or 12. We would prefer the version that gives us the lowest number. Let's move on. We're in part 3 now, question 6. Linkage methods. Consider the following similarity matrix. Note, higher numbers equals more similar. So there's two parts. Part A, if we use single linkage, which is min distance over max similarity, which 2 points merge first? And B, if we use complete linkage, max distance over min similarity after we merge the closest pair, how do we calculate similarity between the new clusters? A and B, and point C. So select one. Is it A, the average? I'm not gonna read all of them, but is it A, B, or C? And a hint for part B that we're using a distance matrix. No, we're not using it. We're using similarity. I'm sorry about that. We're using a similarity distance matrix, not using a distance matrix. So there's a difference between the two. If we were using a distance matrix, it will be a certain answer. But since we're using similarity matrix, it's a certain answer that I won't say right now, but I will now. So let's start with part A actually. So this whole question was assigned to tests if you're basically paying attention to the input data type. So for part A, the first merge, usually we work with distance matrices, but where we look for the smallest number, kind of the closest items. But this is similarity matrix. A score of 0.8 means highly similar, and 0.1 means like very different. And single linkage is the optimistic method, if you remember. It looks for the single best connection. So we scan the grid, right, for the highest number, ignoring the diagonals, 1.0s, and the highest value that we see is 0.8 between P1 and P4. So they would merge first, and that's your answer. P1 and P4, they would merge first. Now for part B, complete linkage is the pessimistic or conservative method. If we merge group A and B, or group AB, we want to see how close they are to point C. Complete linkage demands that C be close to both A and B. It judges a relationship by the weakest link. Since we are dealing with similarity, the weakest link is the minimum similarity. So the answer was C. So I was hitting at this earlier. So if this were a distance matrix, like the problem said about distance matrix, the answer would have been max distance. But since it's similarity, it's min similarity. Always invert your logic when switching between distance and similarity. Now we're actually on a different part 4, which is supervised learning. So question 7, K nearest neighbors. Use the distance matrix in question 4. Assume the training set is A, B, and C, and the test set is D. Label positive, negative, negative. I'll go back just to question 4 for a second. Probably take a picture of this and have it pulled up near you so you can look at it while you're answering question 7. Here it is. So 2 parts. Classify points D using K equals 1, and just fill in the blanks. K nearest neighbor is blank. Predict the class, blank. Part B, classify point D using K equals 3. Nearest neighbors are blank, blank, blank. Majority vote class, blank. So fill in the blank. And here the answer. So if you're looking back at the matrix for question 4, specifically, we look at how the row for D and compare it to our training data, A, B, and C. So the distances were D to B was 2, D to A was 3, and D to C was 5. So part A, when K equals 1, you're extremely short-sighted. We only care about the single closest person, right? The smallest distance is 2, which belongs to B. Since B is labeled negative, point D becomes negative. Just a note, k equals 1 is very sensitive to noise. If b was a weird outlier, our prediction would have been wrong. But the predicted class is negative. Now, for part B, which is k equals 3, since we look for the three closest, since our training data only has 3 people total, all of them get a vote. So now we count the ballots. So B says negative, C says negative, and A says positive. And it's 2 against 1. So since it's 2 against 1, majority vote wins. So the answer is negative. So even though like A, which is positive, is closer than C, in the standard like majority voting, distance doesn't really matter. Only the count matters. If we use distance weighted K nearest neighbor, A might have had more influence than C, but for now we just stick to simple voting. Still in supervised learning, but now we're looking at naive Bayes probability. So let's see question 8. If you are predicting if a server will crash, yes, it will crash, no, it will crash, based on high load the training data. So yes, high load, no, or high load or low. So calculate the posterior probability. Probability of crash equals yes, and the load is high. This sounds a bit difficult, but we're really just counting the frequencies. So here I'll show the answer. The fastest way to do this, if just you have the raw data in front of you, is just kind of just count it. So first, ignore every row where load is low, right? Those rows don't matter right now because we know the load is high. Then now to count the denominator, we look at our data set and see that there's actually 3 instances where the load is high, right? There's 3 of them. This is basically our new universe. Now for the numerator, inside that specific universe of 3, how many did the server crash? Crash twice. So 2 out of 3. So 2 out of 3 times, which give us roughly 0.67. So that's the easy way to do it when you have the raw data in front of you. Now, if you wanted to do this the long way, using the formal equation, you will calculate the probability of crash equals yes, which was let's see, 2 out of 5, because there's 5 total and only 2 of them said yes, so 2 out of 5. Then you would calculate the likelihood of high load and crash equals yes, which is 100%. Because in both times that there was yes, there was a high load, so that'd be 2 out of 2, 100%. You would multiply them and divide by the probability of high load. You will end up with the same number, 2 out of 3, but for like a midterm or maybe a quiz, trusting your eyes and filtering the rows is much faster, especially if the question is kind of laid up like this, and you can just count the rows for yourself. Now, we're at part 5, question 9. So, confusion matrix metrics. Calculate the metrics for this model output. So you got 70 true positive, 30 false negative, 20 false positive, and 80 true negatives. Get the accuracy, the recall or sensitivities, specificity, and the precision. So there you go. Sorry about that. I'm going too fast. There it is. There it is. All right. So this this slide might be pretty important, especially for like a data science job interview. You probably should know these formulas, maybe by heart. The accuracy, all these four. And these are just plugging in, so I'll just go over accuracy. So this is the simplest one, right? Accuracy is how often are we right? So we add up the correct guesses, the 70 true positive and the 80 true negatives to get 150. divided by the total population of 200, and you get 75 or 75%. That will be. Now, just a quick warning, accuracy can be misleading if your classes are imbalanced. Like 90, like there's an example I gave in an earlier video, like 99% of people not having a disease. But here our classes are perfectly balanced, 100 true, 100 false. So accuracy is a very safe metric for at least this problem. And I'm probably not going to go over all the rest of three of these. These are formulas. These are all four have their own formulas to get the accuracy, sensitivity, things like that. Just a quick note about precision and recall. So precision is different from recall. Recall is about coverage, like finding everyone. Precision is about quality, like not making any false alarms. Now, question 10, part 5, evaluation and cost analysis. So cost matrix calculation. So you have this cost matrix, the model results, calculate the total cost for both, and pick the best model. Remember, lower cost is better since benefit is negative. More negative is better. So let's look at the models, the cost matrix in the model. So model A has 10 true positive, model B has 14. This one has 5 false positive, has 15 false positive. This one only has 1 false negative, this one has 5. 80 true negative and 70 true negative. So make sure you use these numbers. Calculate the cost model A, B, and then the best model. And it costs, so you can see, you're basically just kind of doing the math and plugging it in. So let's go to the answer. So I'm gonna have to go back and forth here, but so in real life, especially in fraud detection or medicine, missing a real case, right, like a false negative, these false negatives, is usually much worse than a false alarm, like a false positive. As you can see here, a false negative is 50, right? It's a lot of points. Then a false negative, oh, it's only 5, about 5. So for Model A is conservative. It has very few false alarms, only 5. So basically just annoying a customer, right? False alarms. And you 5 times you said this was fraud when it wasn't, and maybe someone was annoyed, like, hey, well you said I was fraud when it's not fraud. And I'm complaining, but it only happened 5 times, and the cost was 5. So we do 5 times 5, you get 25. Basically, you're doing that. You're finding the cost of all these. So let's go back to Model A. So Model A, they actually missed 5 actual fraud cases. Since missing a case costs 50 points for missing a case, that'll be 5 times 50, so that's about 250, which is pretty costly. So yeah, and then we got 10, a true positive, which is just negative 10. So we got negative 100. Even with negative 100, adding them all together, we still get 175. And that's not good. So positive numbers means you're losing value. Now let's look at Model B. So Model B, more aggressive. It flagged a lot. It has 15 false alarms, which 15, so 5 is 75, so it costs us 75. So 15 annoying people, 15 customers that were annoyed because they got, flagged when they shouldn't have, but that's all right, 75 points. But it only missed 1 fraud case. So it's only 50. That's only 1 times 50, so it's just 50. Plus, it caught more fraud cases than Model A. Model A caught 10. This one caught 14. So 14 times negative 10, negative 140. And the net result is negative 15. So even though Model B had like lower accuracy, it had more false alarms, it is the better business model because it avoids the expensive like catastrophe of missing a fraud. This is like why you can't just look at accuracy. You have to look at the business costs. So of course Model B is better. For the final question, this question is really just you might see this on the quiz or exam. it'll probably just be just explain the 5 steps of PCA. And you probably in a quiz or exam, you most likely don't have to be too detailed, just write down the basics. But this is two-parter, so the 5 steps, but also what's the main purpose of it. And if for the main purpose, reducing the number of variables, features, while preserving the most important patterns, variance in the data. And that's a good enough answer, I think, for a quiz or that's for it, definitely for full credit in an actual test. And then you list the 5 steps, standardize the data, compute the covariance matrix, calculate eigenvectors and eigenvalues, sort of select and transform. So that's basically it. Maybe in the test, you might have to be a little bit more detailed than what I have right now to get full credit. But you definitely won't miss the whole question just by adding these, because these are the 5 main steps. But it might ask you, of course, maybe add a little bit more detail. So you have to do that on your own time, Google it, get as much detail as you can. But that's it for the midterm. And let me know if you did well, or let me know if you thought the questions were good, if they were pretty accurate compared to a real test or quiz that you might get from either college or just a course. Maybe you're taking a course on machine learning and they test you with questions like this. But thank you for watching.